So we are going to be looking today primarily at energy. And we're going to be looking first at just general units of energy. And so we're going to start by talking first about the preferred unit of energy. So the international unit of energy is the joule. But what we're going to find very quickly is that the joule is not the unit that we work with exclusively, nor is it necessarily the best unit for our purposes in this class. So let's look at some alternative units to the joule. Take, for example, the calorie. Now, one thing to be really careful about with calories is that calories can describe about that. Calories can come in a couple of different descriptions. So when we talk about calories with a lowercase c, this is the normal unit of calorie. And by definition, a calorie is the amount of energy it takes to raise the temperature of 1 degree, of 1 gram of water by 1 degree Celsius. Now, as you can imagine, that amount of energy isn't very much, because you would imagine for 1 gram of water by 1 degree, it wouldn't take much energy to get that temperature up. So more often, we end up talking about calories in terms of this unit. And the key thing here is I want you to look at the capitalization. Kilocalories, capital C calories, are the calories that we are the most familiar with, actually. Kilocalories, or capital C calories, are the calories that we put on nutrition labels and on food facts. Tell us how many calories there are in our favorite brand of soda, or in our favorite energy bar, or in our cereal, or whatever. Now, the reason we use capital C calories for this purpose is because each capital C calorie is actually a kilocalorie, 1,000 of those lowercase c calories. And what we'll see is the reason we do this, we're going to do a conversion calculation here in a minute. If we don't use kilocalories for that particular circumstance, the numbers get very big very quickly. So the conversions that we want to become familiar with here are these conversions here. So 1 capital C calorie is 1,000 of the lowercase c calories. That's why we call it a kilocalorie. Now, each kilocalorie is 4,184 joules. And so what we'll often see is that instead of talking about things in terms of joules and lowercase c calories, we'll talk about things in terms of kilojoules and kilocalories, or uppercase c calories. Now, if you're looking for a logical explanation for why we didn't just call calories kilocalories instead, why didn't we just slap that metric prefix on there? I don't have a good one for you. Whenever it was decided just to capitalize the letter C and have that stand in and not change the pronunciation or anything else about it, I don't know. I have I had no reasonable explanation for that, but that is how it is, unfortunately. So those are the more familiar caloric, the more familiar energy kinds of units that we run into. And we primarily are familiar with them because, well, that's how our food labels are written. Now, there are other energy units that exist. So, for example, you'll find things like BTUs, British thermal units, used for things like measuring air conditioners or heating units, furnaces, space heaters, those kinds of things. Kilowatt hours are used for energy. You see this most often with energy bills, electric bills. So if you happen to pay rent or have to pay your own utilities where you live, you're familiar with kilowatt hours because that's how the energy company tells you how much you owe. They tell you, okay, this is your consumption. Here's the rate for your bill per kilowatt hour, and you can see how much they charge you as a result. For conversion factors, for conversion purposes, to do conversions from one energy unit to another, we're effectively going to use dimensional analysis just like we did in chapter 2. Now, your book includes this kilowatt hour conversion to joules. To be real honest with you here, I included kilowatt hours just because it was a unit you might recognize. We're not going to do any kind of measurements of kilowatt hours in the lab or anywhere else for that matter. So don't expect a whole lot there. If it pops up in your homework, that was by accident, not by design. Most of the conversions you're going to see in this homework assignment that's due tomorrow night are going to be between calories, joules, kilojoules, kilocalories. So it's these conversions here that we really need to pay the most attention to. So let's take a look at an example of what this might look like. We have a candy bar. Candy bar says the serving size is going to give you 225 calories. What we want to know is how many joules is that? Now, again, these conversions are going to be on your equation sheet for the exam, so don't worry about memorizing them. But because they're not given to us in the problem, let's just kind of grab what we need to know. We're turning calories into joules. There is no direct conversion for that, at least not easily done. So we're going to go from calories with a big C, kilocalories, to little calories, to joules. So starting with what we have, 225 calories, big C calories. We need to turn the big C calories into little c calories. The conversion here, 1 big C calorie is 1,000 little c calories. Again, big C calorie is a kilocalorie, so that kilo prefix of 1,000 would apply here as well. To turn the calories into joules, the conversion was 1 little c calorie is 4.184 joules. So my calories cancel, I'm left with joules. Now we just do like we did with all of those dimensional analysis problems in chapter 2. Multiply across the top, divide across the bottom. 225 times 1,000 times 4.184. My calculator gives me 941,400. How many significant figures should I round to here? Those of you are giving me the 3, that's correct. How do we know that? Well, we started with 3 sig figs here. This is an exact conversion. And even though this one is not, it still has 4 significant figures in it. We go with the fewest sig figs, so that would be 3. The third significant digit is this 1. So rounding from the 400, 400 would round down to 1,000 as opposed to up to 2,000. So 941,000 joules would be the properly rounded answer.
This question would be like a test or something. Would you give us how many joules equal 1 like kilocalorie?
So I don't think that the equation sheet gives you the direct conversion. So you would have to go through this 2 steps. I think, this slide here does give you that conversion directly. You could use it if you knew it offhand, but again, I'm pretty sure, going off of memory here, and you can double check this when you do the practice test. The practice test has exactly what information you would be given. So I do know that you are given both of these conversions. So that's how I set it up. But yeah, if you're given the direct conversion, yeah, you could use that. Any other questions with this example? So like I said, if you understood dimensional analysis and unit conversion in chapter 2, the only difference here is we're using energy units instead of units of distance or units of volume or units of mass. The concept is exactly the same. We're just changing the units that we're using this time around. But otherwise, we're talking about the same thing. We're talking about the same process. So if you understood it in that application, this is really no different. This is just changing the units that we're converting. Let's have you try one. So converting 9.91 kilojoules into calories. And so the conversion here that you'd want to do, so we want to turn the kilojoules into joules and the joules into calories. Can you connect the dots? So I'll give you a couple minutes to work your way through that, and we'll see where we are in a couple of minutes' time. All right, looking around, it seems like most of us are on the right track. So there are lots of ways to go about doing this. So walking around, I saw some people were going, kilojoules to kilocalories, and then kilocalories to calories. That's perfectly fine. One of the great things about dimensional analysis is usually there are more than one way to convert. So you just got to find the way that works the best for you. As long as you have a string of conversions that are correct and you've set them up properly, you'll get to the right answer. So the way I went about it is I converted the kilojoules into joules. Kilo means 1,000. So there are 1,000 joules, 10 to the third joules in a kilojoule. And then the last conversion, the 4.184 joules in a calorie, that's the same conversion we used in the last problem. When I get to the calculator, I get 2,368 and change. I go back to my numbers here. I have 3 sig figs in the kilojoules. This is exact, so we don't worry about it. There are 4 sig figs in this conversion. So between the two, 3 is fewer digits. So I want to round to this third digit, which means I need to round it up. 2,370 is the correct answer here. Now you can see off of this example and off of the previous example why we don't use little c calories or joules very often. For something as simple as a candy bar, we're talking about 941,000 joules. It's a lot more practical to use kilojoules instead. So we tend to see kilojoules a lot more often instead of joules. We also tend to see kilocalories or big C calories more often than little c calories for this same reason. If I have a relatively large amount of energy, the number of calories is going to be relatively large as well. Keeping this in kilo units would keep the numbers smaller. So this would be 9.91 kilojoules and 2.37 kilocalories, as opposed to keeping the numbers in the thousands here. So any questions about energy and energy conversions before we move off of this topic and go elsewhere? So moving onward then, we want to start kind of bringing together the ideas that we've been looking at from Friday and Monday into today. So Friday, we talked almost exclusively about matter. Monday, we talked a little bit more about matter, but we talked mostly about energy. Now we want to bring those two things together because ultimately, energy and matter are interrelated with each other. When we start to see changes in matter, there are going to be changes in energy as well. And so examples like this work great in physics in describing how energy can convert from one form to another. If I have a really heavy load on top of a building and drop it off of the building, we know that the potential energy that existed on the roof is being converted into kinetic energy as it falls and as it picks up speed. And that kinetic energy is going to convert into other forms of energy once it hits the ground, either in the form of sound or in the form of thermal energy as the result of that force being exerted on the ground and on anything around the ground as well. Now that works great in a physics class, but the energy conversions and transformations that take place in chemistry are not usually this kind of conversion. They're usually other kinds of conversions. So when we talk about potential energy, we mentioned this on Monday. Potential energy in a chemical sense is usually stored within the bonds of a molecule, or at the very least in terms of the associations that one molecule has to other molecules in the same sample. So when we talk about the relationship of what holds water together, water molecules are held to each other in the liquid phase due to these attractions that exist between the water molecules and each other. And when we boil that water, we are going to cause those water molecules to separate, dissociate from each other as they go from the liquid phase to the gas phase. Well, hidden within all of that discussion of association and dissociation, of potential energy being held within bonds, is this idea overall of stability. The natural tendency of all systems is to go toward its most stable form, its most stable state. Now, the most stable state of any molecule is going to be the one that has the lowest potential energy. And so when we encounter systems that have higher potential energy, we're going to notice that those systems have a tendency to move toward more stable states. When that instability comes in the form of the way that the molecule is put together itself, like in the case of trinitrotoluene, TNT, What we will see in those circumstances is that we have a molecule that is generally unstable and will naturally degrade toward a more stable state when it is given the opportunity to do so. So in the case of TNT, if we expose TNT to a certain kind of stressor, some sort of ignition pathway, a spark, some sort of instigator, what happens is that that spark causes a reaction inside of the TNT to cause it to go to a more stable, less potential energy kind of molecule. And the result is we end up with a difference of energy. TNT having high potential energy, the products of its degradation having low potential energy. What happens to that energy difference? Well, it comes out in the form of whatever happens when it explodes. High amounts of heat, high amounts of light, high amounts of sound, and whatever collateral damage comes as a result as well. This is a natural tendency that exists in all systems. If I have high potential energy, whether that is in the form of unstable chemical bonds or unstable nuclear associations, that lack of stability will come out on its own over time. And the result of an increase in stability is usually the output of energy in some kind of way. That's where these energy transformations take place in chemistry. Now, we have two ways of describing energy transformations in terms of reactions. We can describe them as exothermic or endothermic. In exothermic reactions, what we find is that the energy of the reactants is at a higher level than the energy of the products. And so as a result, that energy difference comes in form of the release of that excess energy. A good way to remember this is that in an exothermic reaction, an exothermic reaction means that energy exits. So if we highlight the prefixes here, exothermic exits, we have the same sound describing the same action. Exothermic energy is exiting in the process. In an endothermic reaction, we actually see the opposite thing happening. In an endothermic reaction, the energy of the reactants is lower than the energy of the products, which means that we have to add energy to that system to get it to go to completion. In an endothermic reaction, what we see is that endothermic means that energy enters. So we get that same prefix sound. Endothermic enters. Now, generally speaking, exothermic reactions are more common. And again, if we think about what we just talked about with the idea of potential energy and stability, how things always go to a lower energy state naturally, that makes sense. If the energy is being lowered, then that energy difference has to come out somewhere. And how it comes out is exothermic. However, there are a number of reactions that are endothermic in nature. And the easiest one to think of is the one that we've been kind of pushing on this entire time. Water boil. Water does not boil at room temperature. Why doesn't it boil at room temperature? Well, because the energy of the molecules is such that there isn't enough energy being put into the water to cause them to break away from each other. There just isn't enough energy to do that. But if we raise the temperature and increase the amount of energy that those water molecules have, what we will see is that once we hit that boiling point, once we hit 100 degrees Celsius, now we have enough energy being inputted into those water molecules to get those water molecules to break away from each other and form a gas. That's an example of an endothermic process. In order to get that boiling to take place, we have to raise the temperature, which means we have to raise the energy inside of that sample of water to get it to convert to the gas phase. So endothermic reactions are possible, but they do require energy input at some level in order to run. Exothermic reactions are much more common because, again, it follows the natural tendency of molecules. The natural tendency of all reaction systems is to go to a lower potential energy. And to get to a lower potential energy, we would have to release energy somewhere along the way. All right, so the last thing that we want to talk about out of this particular chapter is the idea of temperature. Now, temperature by definition is just a measurement of the amount of thermal energy that is present in a substance. That is the textbook definition of temperature. How much thermal energy is present in a given substance? And we can tie that value of thermal energy directly to molecular motion. The hotter the temperature is, the higher the thermal energy is, the faster those molecules are going to be moving. The lower the temperature is, the less thermal energy present, the less energy that the molecules have. They're going to move slower as a result. One thing that we do have to do, and this is an important thing to look at, one thing that we do have to do is we do have to separate this idea of temperature from what we just talked about with heat. So again, if we look at the definitions here, temperature is a measure of the thermal energy. Tells us how much energy is in a given sample at a given time. We can measure that temperature with a thermometer. Give us a snapshot of what is going on in that system, in that substance at the time of measurement. Take note of the definition here of heat. Heat is the transfer or exchange of thermal energy. Heat is the result of a temperature change. So if an object gets hotter, heat energy had to have come into that system to raise its overall energy. If a temperature gets colder, heat had to have left that system in the process. So in a lot of ways, it appears that we're talking about the same thing when we're talking about temperature and heat. Understand that there is a big difference between them. Temperature is a measurement of thermal energy. Heat is a result of the transfer of energy in or out of a substance. And when we see that transfer of heat in or out, we will see a temperature change as well. Now, the topic that we're going to get into here is temperature. And as you know, temperature is something that we can measure. We can measure it using a thermometer. The question is, which thermometer do we use? Now, probably the most familiar, because we live in the United States, with the Fahrenheit scale. The Fahrenheit scale, the Fahrenheit thermometer is probably the one that we've used the most often, or in some of our cases, probably the only kind of thermometer we've ever used. The problem with the Fahrenheit scale, though, is a couple of things. First of all, it's defined on some really weird kinds of measurements. 0 degrees for the freezing point of salt water, 96 degrees for normal body temperature. Well, that's problematic for a couple of reasons. First of all, how concentrated is concentrated to give you that 0? And body temperature is 98.6 degrees, not 96 degrees. So a couple of weird issues there. The result of those definitions is that we get water freezing at 32, boiling at 212. And so that represents a 180-degree difference between those two very common measurements of temperature. And so that raises other questions. Why 180 degrees? But we've run into that particular problem in a lot of different ways anytime we've described any kind of English unit. Why are there 12 inches in a foot? Why not 10? Why are there 5,280 feet in a mile? Why not 5,000? Why not 1,000? The numbers on our English scale have never made sense, and they continue not to make sense. And in this temperature application, big surprise, it doesn't make sense. And so in the sciences, we rarely use Fahrenheit. We rely more on the Celsius scale. And on the Celsius scale, we at least have things that are coming out in multiples of 10 again. Water freezes at 0, it boils at 100. This is the temperature scale that we are going to use exclusively when we measure temperature in the lab. It's got a nice scalar mark here. We've got a 100-degree difference between freezing and boiling. That's nice. It's round. It's easy to work with. The only problem is that both of these scales are based on definitions. Celsius scale is based on the freezing point and boiling point of water. The Fahrenheit scale is based on the freezing point of salt water and body temperature. They don't give us a whole lot of picture about that idea of thermal energy. That's where the Kelvin scale comes in. The Kelvin scale sets one defined value, and that defined value is 0. On the Kelvin scale, 0 degrees means that we have no energy. If we have no energy, that means that the molecules themselves can't be moving either. And that's the definition of absolute zero. At absolute 0, molecular motion stops. So if I have no molecular motion, I have no thermal energy. That sounds like a good reason to have something be 0 if it's describing nothing. Everything else is relative to that 0 mark. That's what makes the Kelvin scale superior to the other scales. Now, the question is, well, why don't we use the Kelvin scale? Why don't we measure things in Kelvin? And the answer is this. The Kelvin scale, because it has zero so low, gets into bigger numbers pretty quickly. And it's a lot easier for us to just measure in Celsius and convert it to Kelvin, because notice here, the freezing point and boiling point of water, still 100 degrees apart. It's just set at 273 and 373 instead of 0 and 100. So what this means is that the Celsius scale and the Kelvin scale are effectively the same scale, just that the Celsius scale has been pushed down by 273 points. Well, if that's all that we have to do to adjust is take Celsius and add 273 to it, we might as well just measure in Celsius, which would have much easier numbers to measure, like 0, 1, 2, 3, 4, 5, 10, 20, 30, 40, 50, rather than 300, 400, 500, 600, and so on. So converting between these scales is relatively easy. If I am trying to go between Celsius and Kelvin, the difference is 273. So if I want to turn Celsius into Kelvin, I add 273. If I want to turn Kelvin into Celsius, I just subtract 273. If for some reason I needed to convert something in or out of Fahrenheit, it's a little bit more complex, because in addition to being a difference of scale, 1.8 degrees on the Fahrenheit scale is the same as 1 degree on the Celsius scale, it's also off by 32 as well. So to turn into Celsius, I'd have to subtract the Fahrenheit temperature minus 32, then divide by 1.8. If I needed to go the other way around, that would be the calculation there. These equations are given to you on the equation sheet for exam 1. So again, you don't need to worry about memorizing them, just need to know how to use them. And so where I want to end today is I want to look at one practice problem of just doing simple conversions. If you're looking at the Pear Deck, slide on over to Pear Deck slide number 10. That's the last question that we're going to do. You'll notice that we did skip over a couple of Pear Deck questions. We just ran out of time for those. I am going to put them into the annotated notes so that you can look at them later. I am also going to add to this recording so that we can you can see me work them out as well. But the thing to remember when we're doing conversions of this type is that we want to keep the integrity of the measurement consistent. So in both of these cases, you see that we were able to measure the temperatures down to the ones place. When we do the calculation, we're going to want to do the same thing when we round. So in this case, to find Fahrenheit, we would take 1.8 times degrees Celsius plus 32. (1.8 times -8 is -14.4. If I add 32 to that, I get 17.6. Since our original measurement was known to the ones place, we would want to know this one to the ones place as well. So we would round that to 18 degrees Fahrenheit. The second one, 252 minus 273 would give us negative 21. Since that measurement matches the precision of this measurement in terms of the ones place, we would keep it as negative 21. So those are the things to keep in mind as you're looking at this assignment. Again, the assignment that's due tomorrow night is going to be conversions and temperature scale conversions as well. It's basically all math from what we saw today. So if you answered that last question, that's all I had for you for today. I will see you on Friday.
Sorry.
Okay, bonus questions time here. These were two questions that we did not get into in lecture, but I wanted to make sure that we had worked out examples for on the record. So the two questions are actually related to each other here. So the first one is, we want to convert this Fahrenheit measurement into Celsius. And so the equation that we're going to use is Fahrenheit minus 32 divided by 1.8 is equal to degrees Celsius. Now, again, speaking here from a perspective of precision, 55.8 minus 32, what we have to remember is that the 32 and the 1.8 are both exact numbers. So really to accurately reflect the precision of these significant figures, we're going to maintain the same precision as our original measurement. So our original measurement had 1 decimal place. When we come out of this calculation, we're going to keep 1 decimal place as well. So 55.8 minus 32 is going to give us 23.8 divided by 1.8. Calculator gives us 13.2 repeating. Keeping our precision, original precision of 1 decimal place, we're going to keep that there. 13.2 degrees Celsius is our correct answer there. Now, the second paired deck question that we skipped over asks us to convert that previous Celsius temperature into Kelvin. Remember that Celsius plus 273.15 is Kelvin. So going back to our previous, we had 13.2 degrees Celsius. And we're going to add 273.15 to that. So our calculator, 13.2 plus 273.15, our calculator is going to give us 286.35. And again, just keeping the same idea. We had 1 decimal place. We're going to keep 1 decimal place. 286.4 Kelvin would be the correct result. So these are the last 2 things out of this particular slide deck. So you should have already answered that checkpoint question. And as you can see, that is it for us in chapter 3. So I'll look forward to seeing you in our next class.